I'm going to participate in KForces round. Currently, I'm a bit late for it, but still, I will be solving some problems. Sorting with twos. You're given an array of integers. We can choose m, which is at most 2 to the m is at most 10, or subtract 1. And subtract 1 from all numbers which are at most 2 to the m. For all indices. Yeah. This simply means that we can subtract 1. It's not working. Sorry, I will need to restart it. We can subtract 1 from a prefix, which length is a power of 2. And we are asked whether we can make an array non-decreasing. Okay, to do it, so how is it done? Instead of a1, a2, etc., an, let's consider a2 minus a1, a3 minus a2, etc., an minus 1. So what happens with this array? And let's also think that we have plus infinity after this array. Yeah, so here we'll also have plus infinities. In this statement, we can subtract 1 from any prefix of size power of 2 minus 1. No, actually, we can subtract 1 from any element. So if this is 0th element, if this is the first element, second element, third element, etc., we can actually add 1. We can add 1 to either 0th element or first element or or third element or 7th element, etc. So we can add 1 to element of this form. Okay, and our goal is to make the initial array non-decreasing, so that we want to make all these elements non-negative. So we want all elements which are differences of A to be non-negative. This simply means that we want to check whether all elements except these are non-negative. Let's write it. The number of test cases. Solve test I. Here we read n. Then we read array. And we want to print whether it's possible to fix it. So find ans A, yes or no. How to find ans? We simply calculate the vector b. Which is this. And after that, we want to check that all elements except powers of 2 are non-negative. Powers of 2 minus 1. So we want to check whether bi is non-negative or it is a power of 2 minus 1. How to check that I is power of 2 minus 1? It is simple. We need to end it with I plus 1 and check whether it is 0. So let's check the inverse. So it is bad if both it is negative number and this is not 0. In this case, we have to return false. Otherwise, we return true. Let's check it on this nice sample. I need to open correct input now. Sorry. Yes, yes, yes. No, no, no. Yes, yes. It's correct. So I would like to register for the contest. I cannot do it yet because I'm late. But while that, we can look at the problem being. We have an array of length n. Of positive integers and an array x of length q consisting of positive integers. There are q modifications on the ith modification for each j such that aj is divisible by 2 to the xi. Okay, let's submit. I think it's the first time that I'm late for the contest and I use the extra registration. Nice. Now we can submit. Excellent. I don't like it. Okay, let's try again. It didn't submit. Okay, it's submitted. For now, I will close this. So, we have some array x, okay. Which simply stores the number of bits. And if number is divisible by this power of 2, we add the previous power of 2 to this number. The interesting part is that, so let v2 of n be a maximum number k such that to the k divides n, or equivalently such number that 2 to the k is the 2k is the number of 2's in n. In this case, after each operation, so if we have n, which is divisible by, so if v2 of n equals k and we have an operation with some number x, so if x is at least k, is at most k, then k changes to x minus 1. And if x is greater than k, then k does not change. What does it mean? It means that actually we can assume that our operations are decreasing, strictly decreasing. Why is that? If we have two operations like x and then again x, then the second operation does not change it, because even after, if the first operation doesn't change anything, then the second will also not change it. And if the first operation did change it, yeah, so x was less than k, then after that x would be greater than uk, so the second operation wouldn't change it. Moreover, if we have x and something which is at least x, still this would mean that even if the first operation changes something, then the second definitely wouldn't. So among all operations, we only leave some decreasing subsequence. And after that, what's that? Yeah, and after that, we simply apply all the operations. So we read n and q. We read a and we read x. Then we print the array. Yeah, so we like vi ends equals find dance of a and x. We print ans I. Yeah, and then we print, that's it, that's all we print. So how do we act here? So instead of all vector x, we just store a non-increasing subsegment. Or even decreasing subsegment. So we go through all numbers x. So if y dot empty or y dot back is greater than x, is greater than I, in this case we push it. And then we go through a. So we check, is it true that I is divisible by 2 to the j? To check that, we can check that if we make this end, it is 0. So if it is divisible by 2 to the j, we add 2 to j minus 1. Then we just return it. One, 2, 3, 6, 6, 7, 10, 14, 38, 58, 63, 3, 3, 3, 3, 3, 1, 3, 7, 11, 19. Yes, that is correct. Why cannot I submit it? Ah. Let's continue with problem C. We have n hordes of monsters. In the ith, we have AI monsters. We have two types of attack and a combo counter X. Time limit exceeded in pretest 3. How is that? What? How is that possible? What? How can it be time limit? So we read N and Q. We read AN, we read XQ. Here we... Ah, it should be Y here. It is such a dumb move. It was such a dumb move. Why did I do it? Awful. Okay, don't tell me it will be a wrong answer this time. No, luckily no. Stupid move. But it happens. We choose a number from 1 to n with at least one number of monster, with at least one monster in the horde I. We kill one monster there and the combo counter increases by 1. The second time we choose a number I from 1 to n. Oh, this is an interesting problem. Yeah, so we have two types of attacks. We have some numbers. So like each time we make a first attack, it actually increases by 1 our combo counter, which allows us to make some second attack. Yeah. However, so one would think that the first type of attack actually gives us +2 because we kill one monster and later in the combo attack we will kill another monster because of this operation. However, we cannot like kill half of the monsters by the first type and then apply X to kill the second half of the monsters. That's because these monsters are spread across several hordes. And we cannot kill monsters from different groups with one attack. Yeah, so because of that, we have to cleverly think. So actually, we want to minimize the number of second attacks, but not waste a lot of them. To do that, I think we will need to apply a greedy approach. So we go from the left to right. So if we can kill the rightmost group after sorting, then we kill the rightmost group with the second type of attack. Otherwise, we need to kill one monster from the leftmost group. Okay, it's after this consideration, this is rather quite an easy problem. So what do? We read N and A. Then we print, actually find answer. How to find answer? So first of all, we need to sort it. When we have sorted it, we need to like through 2 pointers, but in different directions. So usually when you have 2 pointers, these both pointers go from left to right. In our case, we will have left pointer going right and right pointer going left. So L equals 0, R equals a like n minus 1, where n is a dot size. So while L is at most R, we do something. So what do we do? And we also have some counter X, which is initially 0, I guess. So there are several cases. Let's firstly consider the corner case when L equals R. So how do we do it if L equals R? So also we have some sort of invariant which says that X is at most the size of our rightmost group. So this is the invariant which we want to hold. Fine. So first of all, we want to kill. So if L equals R, this means that we want to kill some I monsters, then kill X plus I monsters by the combo, and maybe a +1 monster in the end. So this number should be maximal, but at most AR. This means that I should be taken AR minus X half down. And 1. So answer will be if AR equals 1, then it is so if AR equals 1, then it is simply 1. Otherwise, it is this number and maybe +1, like plus AR minus X mod 2. It seems that it is like simply this number. Yeah, so we have AR minus X plus 1. Mm-hmm. Fine. So if L equals R, we also have answer, which we will return. So if L equals R, we say that ans plus equals. So if R equals 1, AR equals 1. We need to, if it is at most 1, let's say then we add AR. Otherwise, we need to add AR minus X plus 1 over 2. Yeah, but no, we also need to apply one operation just for. So the second, this is the first time, number of first time operations. We also need to add 1 to this, so it gets 3. Mm-hmm. And we need to break up to that. Okay, so what do we do here? We need to check whether. So let's do the maximum number of operations which we can. So LL first type, which is minimum of what? So we can either take the whole AL, or we can take AR minus X. So let's do this number of operations. So we add them to ans, and we subtract it from AL. Then we need to propagate. So how do we propagate? If AL is 0, we go to the next L. And if AR is at most X, we subtract from this. So we increase answer by 1. And we go to the left. Okay, let's check. So personally, I would also like to look at several tests of size 1. Like let's see. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Six, 5. No, it's not correct. Okay, for my tests. Is it true for my tests? Ah, of course I forgot to make X 0. And here I forgot to add X to first type. First type to X. 4, 4, 11, 5. And then we have this. 1, 2, 3, 3, 4, 4. Can we believe it? Yes, we can. I believe we submitted. So slow. Not nice. Definitely not nice. Work, please. Yeah. So finally we can look at the standings. And the standings are devastating. What is that? F of x is the floor of the binary logarithm of x. It's like the leading bit, leading one of the x, of f. So let g be the floor of the logarithm of x with base f of x. This is crazy. We're given q queries. The ith query consists of these two integers. We need to print the sum of g of k across all such numbers. Okay. So let's think what we can do about it. We read Q, we read L and R. And we need to print the answer to this query. Modulo this number. I guess what we will do is find the difference between find ans of R and find ans of L minus 1 modulo M. So now we have LLR only. So this returns sum of f in points from 4 to R. Why from 4 and not from 0? Because actually G is not well defined for numbers 1 to 3. So to do it, we will iterate for all I, for all f actually, from 2 to the maximum possible answer. Yeah, which is built-in CLZLL of R and 63 minus that. And for each of them, we want to something like ans plus equals ans of f. So we're asking now how many numbers, what is the sum? So we have numbers like 2 to f minus 1, I think. No, 2 to the f, of course. Etc. 2 to the f plus 1 minus 1. So we have all these numbers. And we want to sum up the logarithm of j with this base. And maybe here, instead of this number, we will have r. I guess we can again iterate over this logarithm, what it can be. Yeah, it's like a number from 0 to 63. And we can count the number of such numbers. Okay, I guess it's doable. So let's divide this problem into several subproblems. 10 to the 5, okay. It's doable. So we say it is sum of answer and product. No, not product, but like find addend from this to this. Now we need to find addend. And also I want f. So now we have the following problem. Let's take all numbers from L to R exclusive this time. Yeah, because I added one here. So we take all these numbers and we want to find how many of them. Actually, I think we do not need this function. We can do it here. So we have this, and here instead of this, we put here maximum of L and this number. I think that it's better performance. And here we just return answer. Great, so here we just need to write this function. And I think we can iterate again through these numbers. So like, first of all, if R is at most L, we return 0. So let's assume that we have at least one number. Then we look through all possible logarithms. So assume that we have a logarithm equal to k. Then we want our number from L to R to be between f, x should be at least f to the k, but strictly less than f to k plus 1. Okay? So let's iterate over the logarithm. LL current power should be 1. So C is f to the power k. It looks like a not nice word, but still it's just f to the power k. So first of all, if C is at least R, then we can stop and return answer. Otherwise, we need to find the new right border. So what we would like to do, we would like to say that if this is number C, then this is number C times F. This would not be correct because it can overflow. So it can be greater than 2 to the 63 minus 1. We do not want to allow this. So instead of that, what we will be doing is say that instead of C times F, we will multiply C prime times F, where C prime is minimum of C and R over F. Yeah, so let's do it. First of all, we take C prime, which is minimum of C, and R plus F minus 1 over F. Then we say that LL C nu equals minimum of R and C prime times F. In the end, we will say that C is C nu. And here we need to add once the number of numbers which are in our current segment, which are like C nu minus C times this number. However, this is not correct because this is not the number of such numbers. First of all, we need to only have here numbers in this segment. So instead of C nu, we will take maximum of ln C nu. And instead of C, we will take maximum of ln C nu. Great. This is still not correct because this is long and the function product takes an integer. So here we need to take %m. Now I believe this is fine. But let's check the sample. Six, 8, 9. Yeah, everything is correct. I believe it should be accepted now. Ah, problem F seems to be much easier than E. So we will solve problem F. We are given a rooted tree. Each vertex has a numerical value. There are operations of two types. Add a children vertex with the number SZ plus 1. Vertex V. The numerical value of the new vertex will be 0. Okay, this is a really easy problem because we can, in each vertex, we can just store what we promised to add to its... No, it's not that easy. So what I would like to do is to say, so assume that we need to add a 1 to some subtree. Let's just add 1 to this vertex, and this will be the promise that later we will need to add 1 to all of its subtree. So if we have number k, it is a promise to add k to all these vertices. And this is not really nice, because if we after that add some vertex here, this should be added k, but this should not. So not plus k. I think it will be fine if we also have the second type of operation, or the third one, which is given a vertex, find its current value. Okay, I think I believe I know what to do. There are two ideas. The first idea is we need to go from the end to the beginning. We will like undo operations, starting from the finishing tree. Okay, so how to undo operations? The first operation is add 1 to a subtree. Okay, so we need to subtract 1 from the subtree. The second operation is to add a vertex, so we need to remove the vertex. But we can just not remove the vertex and simply take the answer which is stored here. So if the answer for this vertex should be ans, in our new tree it will be minus ans. So actually we can still add ones and still have the positive answer here. And then we can simply leave it there. We do not have to remove it from the tree. So the question is, how can we fast add 1 to the subtree and find the value in some vertex. And there is where the second idea comes. This can be done via the thing called Euler tour. So suppose you have some tree. Let's traverse it with some DFS. And we have written all vertices in a row. Yeah, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. It will have Euler tour of this kind, or maybe some other kind. What's interesting is that each subtree will be just a subsegment. So to add on a subsegment, we can just use segment tree. Or maybe even a Fenwick tree. Can we just use a Fenwick tree? So how to use Fenwick tree in such problem? Fenwick tree cannot add on a segment. It can add to an element and find some element. Yeah. Or not find some element, but find some sum. Instead of this, so instead of, like, assume that we have some array 2, 3, 6, 7, 4, 5, 5, 5. We want to add 1 to this array. Let's consider new array, which is 2, then difference, which is 1, then difference, which is 3, then difference, which is 1, minus 3, minus 1, 0, 0. Then instead of adding 1 to a segment, we need to add 1 to this element, and we need to subtract 1 from this element. And instead of finding some element, for example 5, we just need to find the sum of all these elements. And these both can be done in a Fenwick tree. Okay, no more words. Let's do it. So first of all, we need a Fenwick tree. It stores all numbers. Let's make an interface for adding on a segment and finding an element. Yeah, so Fenwick of size n is just an empty array. I always forget what Fenwick stores, so I need to restore that. So 0 is 0, 0. 1 is 1 is 0, 1, I believe. 2 is 2, 2. And 3 is 0, 3. Okay, so we need to add on segment from L to R value V. Instead of that, we will add on prefix R value. And we need to add on prefix L minus value. Okay, so let's now write this function. How to add on prefix. So instead of adding on prefix, we need to just add what? Okay, I just believe we need to subtract 1 from element R. So what does R participate in? It participates in R. So while R is less than A dot size, we say that AR minus equals val, and then we need to do something with R. I always forget what it is. So 0 goes to 1, 1 goes to 3. I think it is R or equals R plus 1. It is void. It is void. And the second thing is add to element. No, not add to element, but find element. How to find an element? So we need to add all segments. So instead of finding element R, we just need to sum up all elements from 0 to R minus 1. Is it true? No, it's not true. If I want to find element 0, I need to sum up all elements from 0 to 1, from 0 to 0 inclusive. So like it, I need to find now the sum of 0 to R plus 1 exclusive. Something like this. So how to do it? So I think simply while p is at least 0, I need to add it to ones, and then I need to somehow decrease p. How do I do it? So 3 goes to minus 1, 2 goes to 1, 1 goes to minus 1, and 0 goes to minus 1. So let's add 1 to all these numbers. And let's add 1 to these numbers. So I think we just subtract the smallest power of 2 in this number. So we have R. We need to take R plus 1 and subtract the smallest power of 2 in this number. To do it, we need to ampersand it with R. Okay, maybe something like this. Nice. So we have made the Fenwick. We have made the Fenwick. Then we need to do everything else. Okay, so we read the number of operations. There are two types of queries. Which can be stored as a vector of parent int. So if TP equals 1, I would like to store -1 and read this number. Otherwise, I would like to just read vindex. I both times subtract 1 because I want 0 indexation. Okay, then I need to print the answer. So how do we find that? First of all, we need to construct our tree somehow. To construct our tree, we would like to firstly to have some structure. So like vvig. Initially, we have only a root. So let's go through all operations. We only need operations of first type in which p of x is -1. For these operations, we need to add a neighbor. So first of all, let's find the number of new vertex. This is g.size. This is g.size. Then I say that g.implies back. So we add a new vertex in the G, and then we need to add it as a neighbor of our current vertex. So we say G of p dot y dot pushback double. I can just do it like this. The code will be shorter, which is the optimal way of assessing a code, is to check whether it's shorter than before. Okay, now we have a tree. Then we need to make an Euler tour of it. The DFS of G. What do we want from an Euler tour? we want to find out like the segment which corresponds to this vertex. To do that, we would also like some kind of timer which stores how many vertices we have already seen. Int timer. So let's pass it. Initially, timer was 0. So again, timer is how many vertices we have already seen. And also we would like to store for each vertex, we would like to know its segment. So let's also make vpii s g.size. We pass it. And this is what we would like to fill. So we say that sv started at moment timer. Then we increase our timer. Then we do it. And finally, we know where our subtree ended. It ended again at timer. So great, now we have the set of all segments which we are interested in. Now we can, and also sv.x is just our vertex. It's number of our vertex in the Euler tour. Now let's store this Euler tour. For that we will have fenwick f of g.size. Yeah, now we need to do all operations in the opposite direction. And we need to store all the answers. Let's go. So for int op index equals v.size -1, op index is at least 0, minus op index. So we look at this operation. Let's look at its x. Let's check if it is -1. This means that we create a new vertex. Instead of that, you just need to store the answer. So we say answer s op index dot y no sv op index dot y, and s is taken dot x because this is the beginning of our subtree. What does it equal? It equals fenwick dot find not 2l but just l, find element on position. On which position? No, not correct. So we have this vertex. And the answer is found for this vertex. But we need to find element, this one. Yeah, because f works in terms of Euler tour, but our ans works in terms of the initial numbering enumeration. So like this. Else, we need to add to a subtree. This should be quite easy. We add on segment from s op index So this is our vertex in initial enumeration. We need to find its segment. I messed up again. So I need this here. So this is the segment. And now we need to print the value which we want to add. And this is simply v. No, this is x actually. Okay, we add this. Excellent. Okay, and then we return answer. Let's check it. Kenvik find L did not work, obviously. This was also obvious. Okay, I have to say it. I didn't expect that. What is the number of test case? This is the very first test case. And for some reason there is a vertex 5. I didn't really expect that. Ah. Yeah. Almost correct. But no. Okay. It's still something that I don't believe. Definitely it shouldn't be like this. Nice. How did it happen? For example, this one. So for root, it is something very clear. We just added 3 to the root and then 4 to the root. Okay, this is... No, this is fine. So we have some sort of Fenwick tree, which stores all zeros. Then we add from the end to the beginning. Okay, this totally did not. Okay, 4. This is fine. Now it should be 7. Okay, now it should be 7. Okay, it is 7. Ah. What? Dude, that's trash. Ah. Okay. Actually, what I really needed to do here is to store the numbers of elements which correspond to some operations. So let's do it. Nums of v dot size, and here I say nums dot pushback g dot size as well, and else nums dot pushback 0, like for example. And here, what I really need to do is to store nums of index. And the same is here. I need nums of op index, then I need to renumerate it by s, and I need to find the element. Now this element will be 0. That is understandable, because I also needed to say that ans0 is f.findL of 0. Unfortunately, because 0 is not anyone's nums, so it was never added in the tree. Again, what's happening? 758, 62, 101, 14, 14, 4. Yeah, as always, I wasn't really fast. Or even medium. I was slow. And I was incorrect. Maybe that is because... Yeah, long. So notice how easily my wrong answer becomes accepted. I just replace this. Replace this. Replace this. Replace this. Replace this. I think that can be enough. Let's recheck. Let's recheck. So we have Fenwick. We either find element to the long Hans, or we add this number on segment. It should be fine. We can also have just make a test which says like 5 or even 6, and then we just ask to add -1 billion. No. Yeah. And it says now the right answer, and before that it wasn't so obvious. And now we also only need to solve problem E. 37 minutes. Maybe he also forgot long. Python? No, C++. This is so slow testing. Fine, we will solve problem E. Brukhowicz and exams. So n exams are administered. For each exam, difficulty is known. We don't want to GCT be 1. The sadness of the academic year is this number of consecutive exams. Sadness numbers of indices E such that this here. Wants to minimize the sadness of the year. Can set the difficulty of any exam to 0. No more than k times. Helps Milo determine the minimum sadness that Brukhowicz can achieve if he performs no more than k operations. Isn't this just a DP problem? So we have an array. Yeah, we have an array. And we want so we have an array. Yeah, if there are two elements which do not have GCT1, so their GCT is greater than 1, then we can simply look at this part and this part separately. They are not, they don't cooperate in any way. So now let's assume that we have several arrays where all numbers are, all consecutive numbers are relatively prime. So also let's look at any 1 and notice that if you do not replace 1 with 0, it will be bad because its GCD with its neighbors will be 0. It will be 1. So all 1s should necessarily be replaced with 0s. After that, let's do the same thing. So in the beginning, we can replace all 1s with 0s. And then we can look at all such segments of relatively prime numbers. In such array, we need each second number to be replaced with 0. Actually, this problem is much easier than F. Why do people solve F instead of E? Is it trolling? Is it some sort of trolling? So we read N and K. No more than K times. Okay, this becomes interesting. So no more than K times. Okay, but still. So okay, let's consider several. As I said, if we have two numbers which are already relatively prime, we can replace this problem with two problems. So now we have several segments, And in each segment, all pairs are sad. Yeah, so all pairs are sad. Yeah. And each operation can either remove 0 sad pairs or 1 sad pair or 2 sad pairs. And this only depends on the ones. Yeah. So if you have a pair with 1, then making this 0 will still leave this pair sad. But if it is greater than 1, then it will become non-sad. So maybe this can be considered as a graph, bipartite graph, yeah, in which there are several edges and also several vertices. So there are several edges and some vertices are called highlighted. We want to choose some vertices so that each edge is either removed, but if it is if it has a highlighted edge, then highlighted edge should be removed. Interesting. Interesting. Okay, so we can consider it as the following sequence. So several non-ones, then several ones, then again several non-ones, then several ones. So first of all, we just need to remove every second of these elements. This is what we need to do. Remove every second of these elements. Yeah, because each of them gives us +2 to the answer. Also, if we have only one once here, only one, we need to do that also. Even firstly, we need to remove all ones, all blocks of 1, 1. Yeah, after that, we need to remove all such things. We need to remove all such things. Okay, what next? After that, So what? So we have some block of non-ones, which can be maybe surrounded with ones. Yeah? So after we have removed every second of them, yeah, so let's look at some block. So if it is odd, 1, 2, 3, 4, 5, then we remove these two elements. And now each of these elements just gives us +1. Ah, no. No, actually no. We are totally not interested in this element. For example, it does not give us +1. So in this case, we just have +1 for this. Ah, I got it. So if this is an odd block of non-ones, we just don't touch it anymore, because instead of touching this element, we can as well touch this element if we like. And if instead of touching this element, we can as well touch this element. Okay, if this is an even block, we would like to touch this element as well, and this will give us +1. So first of all, we take all blocks of non-ones and all blocks of only one ones, and we add, you know what? Okay, after that, it becomes quite interesting. So we have block of ones. There is also one corner case when this block of ones touches the left side. Usually it doesn't, but sometimes it does. For two blocks, maybe. Okay, in this case, so we take the smallest block of ones and we try to eliminate it from one side to the other side. Yeah, we try to eliminate it. And if we do, we get additional +1 to the answer. Yeah, great. Great problem, very interesting. A dream. Let me think. Okay, so let's write it. I have a lot of time, I believe. So we read T, we read N and K. We read A. And finally we need to print answer. Okay, I think we will make this. So what do we need to print? Minimum possible sadness that we can be achieved by performing no more than K operations. Yeah. Actually, I believe we can just perform the correct operations. I think we just can just perform the correct operations and calculate the answer in the end. So let's do it. So what we will do is, in the end, we will go through all the elements. And say that if GCD vi and vi plus 1 does not equal 1, then plus sans and return nice. Nice. Is it correct function? Yes, this is a correct function. It's based. Yeah, because some people use this function, but this is not correct function because on zeros it will fail. And my function does not fail on zeros. So we only need to make k operations here. And that's it. So let's do it. We go through all elements. Actually, I failed here. I needed n minus 1. Great. So we look at let me think. Let me think. So let's start with an easy case. So assume that if vi is not, also let's say that k and this. So assume that vi is not 1 and vi minus 1. I also think we should do like this. So we consider all inner elements. So if 3 elements in a row are not ones, so I even think we cannot ask about vi. So let's assume that we have an element which is not 1, and the element after that is not 1, but both GCDs are 1s. GCD of vi minus 1 vi is 1, and GCD of vi plus 1 vi is 1. So in this strange case, we can subtract 1 from k and say that vi is 0. Okay, we did it. After that, we need to iterate over all blocks of 1s and eliminate them in the order of from the smallest to the biggest. Okay, let's do it. So first of all, let's find all blocks of 1s. So we have vector pair and int. Vector of pair of int and int. Okay, I believe this is the size of the block and this is where it starts. 1s. So let's go through all elements. Let's go through all elements. Yeah, so if vi is 1, then we do something. What do? We check whether our current block is neighboring to our 1. So if 1's not empty, and if we take 1's dot back dot first and plus 1's back dot second, if this is I, then we need to increase 1's dot back dot y. Otherwise, we need to 1's dot emplace back. What? The size of the block? No, sorry. I think it is x here. We need to make a new size of the block and the position of this block, like this. Great, now we need to sort in increasing order. Now we go through all the ones. So for int const pii 1 of ones, we do the following. So we say if k equals 0, then break. Then we iterate through all ones. So like this. So if 1 dot y equals 0, then we need to go from bottom to top, from the last element to the first element. For int I equals 1 dot x plus 1 dot y minus 1, I is at least 1 dot y minus I, and also we check that k is not 0. So while this is true, we say that vi equals 0 and minus k. I even believe we can minus k here. Yeah. Else we do it in increasing order. So we start in 1 dot y. We say that it should be less than y dot 1 dot x plus 1 dot y, and plus I, and again minus k, and the same thing. Great. Now we have iterated through all ones, and last but not least, we just need to iterate over all elements which are broken. To do it, we go just through all elements, and we ask, is it true that I is greater than 0 and GCD of AI and AI minus 1 is 1? Or is it true that I is less than n minus 1 and GCD of AI and AI plus 1 is 1? If this is true, we also need to decrement k and say that AI is 0. V. Yes. Okay, I believe that's it. We even have 12 minutes to test it. 3, 4, 5. What? Minimum possible sadness. Okay, in this case, this. is 102, 205. Okay, this is incorrect. The sixth test. Sixth test. Okay, we need to look into it. So we have 7 operations. Let's look what I would like to do with it. Let's look what I would like to do with it. So definitely 1. No, I wasn't paying attention. So we have this block of numbers. So I do this. Then I don't do anything really. Here I have block of numbers and I do this and this. So I have done 3 operations. Then I look here and then again, now I do a 4th operation. Yeah, now I have 3 operations more and I sort all blocks of ones in increasing order. I start with this one and I make it 0 and 0. And then I make 0. I understand what happened. I don't want to look at the segments of ones which touch the border. I don't want to consider the ones which touch the border. Yeah, so they are considered in the end, I think. So, okay. Let's make a custom comparator. Okay, what do we do? First of all, we need to check, is it true that one of them touches the border and the other one doesn't? So, if 1, 1, how to check that it touches the border? Either its y is 0, or its x dot plus y is n. So if this happens, then 1, 1 touches the border. Let's check the same thing for the second one. Oh, let's check that it is not the same for the second one. So for this one, we check that either it touches the first border or the second border. So if this is not the same, then we preferably use the 1, 1 if it doesn't touch the border. We return that second touches the border. Otherwise, we just return 1.x less than 1.2.x. Actually, thank you, authors, for the nice test. Now I think it will be 5. 5? Now it's 4. Four is definitely incorrect. 4 is definitely something terrible. Why is it 4? Let's look at the array in the end. Well, what? 4? 4 when it said 5. Yeah? This means that something is really broken. How is it 4? I don't think it can be 4. 1, 1, 2, 0. So the correct answer is this. 1120 455 66 08010 0002019. Okay, there's definitely 5 pairs here. One, two, three, four. Stop, what? So are you telling me that there are only 4 pairs? One, two. I'm really confused. So let's again copy this test. Now it's 5. Ah, this is because it's not 19. Okay, whatever. Let's recheck everything now. 102, 205, 521. Let's try again. Now I understand why people preferably solved F rather than E. Because in some way it's really simpler. What's wrong? Why it's 778? Did it make like 5 incorrect and 10? Dude, 10 incorrect attempts. Oh my god. Okay, I solved all problems. I solved all problems. Great, now we can make an editorial, of course. Okay, I think I will make a tutorial in separate videos.